Hello kids, today we will be reviewing Unit 6 of Grade 7 Science, which is light. Let's get into this. This is the first topic in the series, in which we will be discussing reflection of light, right? So what do we mean by reflection of light, right? As you can see, this is a laser image I've taken up from the internet, in which here's the green laser which we're projecting. There's one mirror on this side, right? And there's another reflecting surface which this person who's put us the setup has placed it over here. As you can see, it's reflecting, right? The laser is bouncing off through these reflecting surfaces, and this is where it goes, right? If I draw the arrow vectors from here, it is incident, right? And this is all the way where it got reflected, right? And inside this is what we can call as total reflection, right? In which, in other words, light is not able to move out, but it's just simply bouncing off, right, on multiple surfaces. Now, let's see how light does bounce off, right? When we look at the reflection of light, the light ray which is coming onto the reflecting surface, which is in our case is the mirror, is what we call as the incident light, and the angle it makes to the normal. Now, what is a normal? Normal is a perpendicular line, a line that makes a 90-degree angle to the surface. Any reflecting surface is called a normal, right? So if this is the normal, then the angle that it makes to the normal is called the incident angle, right? So let's call this as incident angle, right? And just a minute, yeah. And the angle that it makes after reflecting is called the reflected angle, right? And the ray would be definitely called reflected ray because it just got bounced off. It reflected off this reflecting surface, right? So these are the three things you need to remember. Reflection, no, let's call this reflecting surface, right? Right? Okay. Now, when we are talking about reflection, we come across a law of reflection, right? Now, what does the law of reflection suggest? That this angle I, right, this angle I should be equal to angle R, right? Now, in class, if you remember, on the board, I wrote these as theta I, theta being the angle, right? And theta R, right? They're just representing by I or R. You can represent that as these. So theta represents angle, right? In mathematics, it's a mathematical symbol that I've used in the classroom, right? Now, reflection can be done on different surfaces. We discussed that we use mirrors of different sorts. Plane mirrors generate plane images or straight images, right? But we also have curved mirrors, which we have concave mirror over this one, right? And the convex mirror, which is the bulged out and the bulged in, right? So this is curved in, this is curved out, right? So these are the two mirrors. We see those mirrors on the road. We have discussed about these safety mirrors on hill roads where you cannot see the incoming cars due to the sharp turns on the hills, right? And this helps you see around the corners at a larger area. Then we have these magnifying mirrors, which are also convex in nature, right? Convex can give you a smaller picture of a very larger area, or can help you see a larger area on a very small surface, right? It's the same thing around. Okay. Then we discussed about these fun mirrors, or the mirror houses, right? uh, Mirror fun house. So how does that even work? How we get different shapes is that we use a combination. As I discussed in the class, we use a combination of these curved mirrors, in which we have the plane mirror, which is giving you the same size image, right? And then on across the lower part of the body, we have the convex mirror. If there's a convex mirror, it's a curve out mirror, then we'll see a shorter image, smaller image. And if there's a concave mirror, we'll see an enlarged one, right? So you can easily detect from here, right? This is some sort of, yeah, this one, that this is some sort of this arrangement that you see, right? It's the first one that you see. These are different arrangements, right? So this is what we call as reflection. Now, reflection images in the workbook, we saw that at different surfaces, light reflects in different angles. So whenever there's a ray of light and you're asked like this is the incident ray, right? This was the question majority of you were stuck on. So remember that you have to make the normal perpendicular to your uh, you can say this is the 90-degree angle, right? Your line should make 90 degree, which we call as normal. So draw a normal at the point where the light ray is coming, right, on the surface. So this is surface 1, right? So on this surface, so then we're going to draw the reflected ray at an equal angle. Just measure this angle I, right, and then draw a similar angle R, mark it with the D, right? So wherever it is reflected back, just trace it, put an arrow there. Now on this surface you have to draw the normal again, right, like this, and that should again be at 90 degrees with this surface, right, because this is where the light is falling at this point. And from here we're going to draw the exit ray, right? I'm going to take the orange one now. So this, remember, this again I should be equal to this R angle. So we're going to use the D to mark this and then draw the line using that trace, right? So this is where the ray of light will exit, right? Then we had another case in which we had a pipeline. So the initial ray was drawn like this, right? So what you needed to do was draw the normal, right? I'm going to use now the purple one. Here's the normal to this surface, 90 degrees, right, with the D, and I'm going to take this angle I, draw another equal angle R due to the law of reflection, draw this, right, and again on this surface I'm going to draw another perpendicular. I'm now just going to be rough with it, right? So again it will keep on reflecting, and remember, don't reflect it on your own. You have to draw these 90-degree angles to represent where it is going, right, like this. So this I should always be equal to this R, right? This is called reflection. Now this is total internal reflection that I'm talking about, right? Total reflection, that an light ray is trapped inside two surfaces and it's just bouncing off till it gets exited on the other end, right? So remember to draw these light ray arrows, right? Remember, light rays cannot in such a case reflect out or refract back, right? Do not mistake this as refraction. Don't mistake for refraction. Now what is refraction, right? As you remember, we were doing experiment with the prism, right, and the mirror. We saw some of the light rays which were extra, right, in extra directions, and one of the light ray was passing through, right? So this is the experiment we went through in the lab. So this is what we call as refraction of light, right? So what is refraction of light? We can say it's the apparent change of image due to changes in medium. And what we mean by the medium, right? What is medium? So medium over here is this water and this glass, right? And in this normal case we have just the water and the air, right? So whenever light shifts from one medium, which is air, into water, which is the other medium, its speed changes, right? So speed of light changes, that results in change of angle, right? And which is the angle? This angle, right? In reflection we talked about that the ray of light will come and bounce off at the same angle. But in case of refraction, since it's changing medium, it was coming in from air, now it will enter into water. So inside water, the light travels a little slower than the air, and because of that, it will change its angle, which will make you feel that the apparent depth of this water is less, right? So we see an apparent image of the bottom of the water, right? We can say the bed of the sea or the bed of the river. It appears to be shallower while it is quite deep, and this happens due to this apparent change of angle of light, right? Why does it happen? Because the speed of light changes when there is a medium change, right? And it depends how fast or slow it's going, right? So whenever it's coming from uh, and a less dense medium into a more dense medium, right? More dense or slower medium. So light ray has to get faster, so it will have this angle of incidence in which it was coming in, right? I'll use this lower angle. If you remember this glass one that we did, right? So this was the incident angle which was formed with a normal to this surface over here of the glass slab, right? And we saw that the laser was supposed to go here, but it did not appear here. Instead, we were able to see at a different range, right? When we removed the glass slab, this was the ray that was followed, right? But with the glass slab on, this is where the ray was exiting, right? What was happening inside the glass? That it was shifting path, right? So we set up a rule that from less dense to dense, right? Denser medium. So what happens? Your uh, it moves towards normal. And as you can see that the ray of light, this is the normal, right? The ray of light which is making this larger angle is now making a shorter angle, right? So it moved towards the normal. This is the normal line coming in which I'm projecting, right? And that is what is happening when it gets from a less dense medium into a denser medium, right? Which is glass, which is in which the speed of light is slower. And now when it is exiting, this is the angle, right? Again, this is the normal, this dotted line, right? As you can see, the angle as it exits into the air is now greater compared to what is over here. Now this is going to be the incident angle from the glass into the air. The angle has changed. So when we say that if it goes from denser into less dense, right, it moves away from normal, right? And that is what we see, right? So this is what we need to discuss when we're discussing this, right? So if case you in case you have to draw this, so just draw a normal onto the incident ray that is coming, right? This is the incident ray. As of rough, you just need to bend it towards the normal, right? This is what you need to do. Just don't exaggerate much, just give it a little bend, right? And when you're talking about the exit, all you have to do is to draw a simple normal again to the point where the light ray was coming, right? This the green one is a light ray coming, right? Just draw this normal, this purple one, and you have to make it move away this time from the normal, so it will become more sharper, right? Like this, away from the normal, right? In this case, it was moving towards the normal, towards the purple line. It came towards the purple line, it went away from the purple line, from dense to less dense, right? And from less dense to uh, more dense medium, right? Okay, this is what we did in the lab, right? And this is the additional reflected ray. This is the total internal reflection as well, right? We will discuss this as a additional content, not part of your syllabus though. We'll discuss it in class if you got free time in the lab sometime, right? While doing this again. So this is another image from a semicircle, how light can be reflected, right? And all, if you can see, is if I draw the normal over here, this white, this is the normal. So this white light is having a larger angle, and over here it's having a lesser angle, and over here it's coming out straight. Why it's coming out straight? Because at this surface the normal is this way, and whenever light comes at a normal angle to any surface transparent from maybe from less dense to a denser or from denser to a less dense. It doesn't matter if it's coming at 90 degrees, it must go at 90 degrees. This is what we call as Snell's law. Although this is not part of your syllabus, but just for your understanding, that I'm telling you, when it comes at a 90-degree to any surface, it doesn't matter if there's a medium change, the angle does not change, only the speed changes but not the angle, right? Why? Because it's already coming straight, so it's not going to have any angle changes, right? And if it's coming at a very slight angle, there would be very slight changes in the angle as well, right? So this is a bit about refraction. Now, one of the applications of refraction is the optic fiber, right? We know that in optic fiber we see total internal reflection, right? And how does it happen? That we use two different type of mediums, right? Two different types of glasses. One is called the high index core, where the speed is slow, right? And then we have a lower index cladding, which is in which the speed of light is a bit faster, right? Since it goes faster, so the light ray which comes at this acceptance cones, or this angle at which the light can be preserved inside the optic fiber, this is not delivered, but the one that is coming at a certain angle, I will draw the normals over here with the purple pen. As you can see, it is only making equal angles, right? So this is total internal reflection. Once it's totally internally reflected, it cannot go out any further, right? Not possible. And secondly, it should always make equal angles, right? So the law of reflection must be followed. Even though this is supposed to be refraction, but refraction at certain angles, in certain cases, when the arrangement is made between a slow and a faster medium, we can totally internally reflect. And this, you remember that once you look at the water surface, at times you're able to see images on the surface, right? Inverted images of objects, trees, and any water, ponds or anything, right? That is reflection from the surface of water. That is, although water is transparent, but why do you see it reflecting? Although it's not a mirror, it's due to this factor that it's the combination of the slow and the fast, and the angle at which we call as acceptance angle, at which we just put it through, it will remain inside one medium, reflecting back and forth, right? So this is how we can do use optic fibers. What are the applications for this optic fiber? We can use this for medical purposes, right? We can see internal tumors and stuff. We can use this for diagnosis. Then we have industrial uses, right? To detect any problems in the structure, in the bridges. We use these to see if a bridge is being cracked from somewhere. If it does, there would be no light coming through because it would be cracked from somewhere in between, right? In case the bridges break out in some concealed manner, we're not able to see those cracks, but inside it's cracked. So these optic fibers, we place them while constructing such bridges inside them in advance, so that in case if the bridge cracks from anywhere, the loss of optic fiber can be used to detect those cracks. And finally, we have instrumentation and communication, right? Instrumental for engineering tools, right? We use optic fibers. And then communication, right? Which we the GPON, the internet that we use, is also now delivered in optic fiber. And why it is extremely fast? Because light is the fastest traveling object in the universe. So I think the fastest way to send signals, I mean, we have conductor wires, telephonic wires, which deliver internet to us, but they're slower compared to the optic fiber. The reason being that electrons travel slower than photons, which are the packets of light, right? We call the particles of light photons, right? So moving on, making rainbows, right? Now, how we can see rainbows? For this, if you remember, we did this prism experiment. We saw that Ayan was doing something with the colors, and we were able to see several colors. He was putting sunlight at a certain angle, in which he was able to create these colors, on the lab wall. So this is what we call as dispersion of light, right? Now, dispersion means converting white light into the spectrum of light, right? And why we call this as a spectrum? Because it's a collection of several waveforms, right, of light, right? And the spectrum, this is what we call as the visible range. And why the visible range? Because humans can only see this range of the spectrum. There are others, right? Above we have infrared, we use on the remotes and stuff, and then we have the UV, ultraviolet, which is blocked by the atmosphere. This is dangerous, right? You get both of these IR and UV and this white light from the sun, right? That's the majority of the sun's light which comes into the earth, and but this is blocked. This UV is blocked by the ozone layer, right? Now, this is the reaction that you get from raindrops. So let's say if there's the sun, right? Uh, Here's the rain, right? Having somewhere, and you're somewhere in between, right? And you're looking at the rain, and there is the sun. So what really happens that the light from the sun is coming towards this, right? So when it comes onto the clouds and stuff, you can see there's some bright glow, but when it comes onto these rain droplets, it disperses, right? This is the same prism effect that is being done by these water droplets that's converted into the spectra, and that spectra gets reflected back towards you, creating the big rainbow that you see, right? And you've seen if the clouds are farther away, the larger you see the rainbow, and if the clouds are closer to you, then you see a smaller rainbow, right? Smaller rainbows will be forming around you, right? This is how the rainbows are formed, and this dispersion. Now remember these colors. I told you that I remember this in the reverse order, which is the Vibgyor, right? Violet, indigo, blue, green, yellow, orange, red, right? The other way around can be remembered. I just remember it from the, you know, the fastest towards the slowest, right? This is the speed range, and why violet is at the bottom? Because it's the fastest, so it will have the fastest change in the angle, most change in the angle. As you can see, if you draw the normal, you can see different lights are reflected at a different angle, right? So these refractions, the change in angle is due to the changes in speed. Red is the least energetic and it's the slowest compared to this violet, which is the fastest and has most energy, more energetic, more dangerous, you can say, unsafe. So violet light is, that's why it's not used anywhere, right? It's not recommended to be used because it's very closer to UV, and most of the violet bulbs also produce UV, so which can cause cancer. So you only see these blue ranges and above, right? Not the below. You don't find these in commercial lighting systems. Why? Because these are dangerous, right? So these bulbs are not produced. And why these are different? Because of the changes in speed, different changes of angle occur due to differences in the speed of these waveforms, right? And this is how, as I said, different rainbows are formed. And as you can see, the closer one is brighter, but it's sharper, brighter, and it's smaller. The farther one appears to be dimmer because it's a bigger image, it's more diminished image, right? But it's enlarged, right? So this is what you get in terms of rainbow. Moving on, colors of the spectrum, right? I've given some of these advanced images, right, compared to your book, because I think you guys are smart enough to understand what the visible range is. And this is basically the complete spectra, right? Spectra means this is the complete range of radiation sent by sun, right, during the fusion reaction, and out of which most of these are blocked. These which I'm crossing out are blocked already by the magnetosphere of Earth, right? What's the magnetosphere? You can check it out. Again, as I said, this is I'm telling you some bit advanced knowledge, not much to your testing concerns, but just for the understanding that these are blocked, and we can only see this range only, right, from 700 nanometers to 400 nanometers, which is the violet, right? So again, I'm going to write the RGBs on this. So this is red, orange, yellow, green, blue, indigo, and violet, right? So this is a Vibgyor that you can see. Humans can only see this part of the spectrum, right? And out of these, the increasing wavelength or decreasing speed, we can say, right? We can say decreasing damage. So that means red light is less damaging than blue light, and hence we see red lights also travel farther compared to other lights, which would refract more and would be diminished earlier compared to red light, and hence we use these as brake lights or emergency lights, right? As you can see, red is considered as an emergency light for a reason, because it's first of all least damaging, and it's more alerting than other lights, which would be more irritating in nature, especially the blue light, which usually has this glare causing effect, which can have eyesight issues, eyesight problems, due to this. So there's blue, safer blue range as well, but the more blue that we use, we cannot control these that easily though, right? These are very expensive lights, which are just these good blue lights, right? Normal blue lights we find in the market contain the complete range, which is some of it is also HEV induced, retina damages and cell death caused by these brighter ranges of the blue, which is a bit damaging, right? So this is the light bulb experiment we did in the classroom, right? And this is the spectrum that Ayan was doing with the prism over there, right? We tried to do this in classroom as well. Now, the color combination models, please, I would want you to remember these. This is important. This is the RGB model, right? The red, green, blue model, how these combinations create them. We have done this in class, as I said, with the paper color experiment, right? So when the green and the red mix up, they create yellow. When red and blue mix up, they create magenta. This is called addition of colors, right? So when we talk about addition of colors, this is what we get. Then when the green and the blue mix up, we get cyan, and if we make all three colors, the red, RGB, or these magenta, yellow and cyan, we get white, right? Now this is the addition one. Then we have the subtractive one as well, right? So I will tell you about an article to read. I mean, there's an amazing article how different subtractive and the addition color works, right? Go through this. I'll share the link. You can easily check the link from this description, right? It's available. I've taken this snapshot from there just to show you that this is going to be an amazing read for you people. Just go there. They've done an incredible job explaining how the colors work. Now we are going to discuss color filtration, right? So if you remember, when we talk about color filters, we were putting light on different surfaces, and if we try to filter those, what really happens, right? So if there's a yellow paper, right, and we put white light on it, we will see red and green coming out of it. And why is that so? Because in color addition, we studied that if we mix the red and the green, we get yellow, right? So that is what we get. So the blue is absorbed, right? The blue is crossed off. The yellow will absorb the blue but reflect these two, which is yellow light, right? So you will see yellow light coming out. And if you put a green filter later on, you will only see green light coming out of it, right? So you will have green light at the end, right? So more, this is what it means, right? This one. Now, as of exercise, let's try to do this. If we have white light, we put a red filter over there, we're going to get red light over here, and all the other, the green and the blue are crossed off. Why? Because the red filter will only allow the red to go through, so we will get red light, but ahead of this we will not get any light because blue will block red as well, right? So we will get no light, right? These are just color filter exercises, right? Let's say if we have got white light, now we put a secondary filter, which is magenta, right? So what is magenta color? Let's review the addition. Magenta is by red and blue, right? So it will allow magenta light M to go through, which is blocking green color, right? Because red and blue are passing through, right? They're going through, which causes the magenta color to come out, right? And later on, since there is no green, so green filter will only allow the green to go through, we will get no light again, right? So it will block all light. Now if you go white and we've got cyan, so it will allow cyan light to go through. What is cyan? It is a combination of green and blue, right? So when the green and blue mix up, they create cyan, so red is blocked this time around. And yellow, over here we've got yellow filter, so yellow is a combination of red and green, right? So what are we going to get? Red is already blocked, so we will only get green light over here at the end. So this will have some light, but only green. red was blocked over here. Now the yellow one will block the blue light in the cyan, so only green would be going on, right? So this is how the light subtraction and addition can work. This is a fun process to go through. As I said, it's a beautiful read. Just do go through this content and you'll enjoy this read. The final topic in this unit is the galaxies, right? And this is the most fun topic. This is I was talking about in the classroom, that if you look at the night sky, this beautiful anomaly in the sky, this cloud which appears to be very far away. It's not our planetary clouds. This is something in space, right? Big cloud. We cannot see this. We can see this from North Pole or very high areas or the South Pole. We can see this. So this is the galaxy we live in, right? And this galaxy, right? Sorry. Yeah. Okay. This galaxy over here. Uh, it's just one tiny little bit, or you can say a portion of our own galaxy that we can see. So how does our galaxy look like? This is how our galaxy looks like, right? This is where we are, somewhere here in one of these spirals, right? Far, far away from the galactic center. This is called the galactic core, right? This is a spiral galaxy, and as you can see, we've got two spirals, right? One and two. So it's a twin arm spiral galaxy. And how do we know? I told you that we can't see our own galaxy, unfortunately, because we're sitting in it. So, but we can see out of the window different galaxies. But how do we know how our galaxy is designed? We did a star scan, right? And the star scan, the density, the arrangement of the stars, and their location data, the infrared sensors, they told us that this is how our galaxy is supposed to look like, and it is actually a spiral disk, right? And this is what the spiral disk from one of the poles look like, right? It looks flat. So the central black hole of the galaxy, the molecular clouds, the spiral arms, the star forming region where still smaller younger stars are formed. We are a younger star because we're on the outer edge of the galaxy, telling us that we're newer compared to these inner stars which are very old, maybe million billion years old, right? And this is the galactic bulge where the large lump of gas and stars, exploding stars is. This is where the black hole is consuming, or what we say is spiraling this you know uh, galaxy. So this is what we have. This is a galactic portrait. As I said, we don't have the image of our own galaxy, we do have the images of other galaxies, right? How the galaxies are formed. So we've got different clouds, different nebula, right? Nebula is a glass cloud, right? It contains rocks, gases, right? And you can say dust, stellar dust we call it, right? So I'm just going to call it a stellar cloud, right? Large stellar clouds, extra gigantic large stellar clouds, in which things join together, collide together, forming these bright stars, right? Causing fusion to form, and ultimately causing stars to form. This is what we call as star formation. Star formation occurs, and those stars then they start colliding, exploding, making new things, and this is what we call as cloud collapse, right? In general, and I would call this as nebula or nebula collapse, right? And when it does collapse, it forms a galaxy, right? And how the galaxies are formed, there are different shapes. As I said, ours is spiral, there are others. So if it's just a simple pinch and this is an explosion, we get an elliptical galaxy. And if we have a larger spin rates, right, it starts to form like a cutting disc, right, like a blade disc, and it appears to be this spiral galaxy like ours, right? There are other shapes as well. I've told you about the elliptical, spiral, then we have irregular. These are the real images, as you can see. This is M101, right? This is very far away. It's another spiral galaxy which looks like our own galaxy in terms of star formation, right? And then we have irregular galaxy, right? The star factories and other very high energy, very bright galaxies out there, right? Please go through this series of YouTube videos which are available by National Geographic, right? This is Universe 101. It will tell you all about our own solar system, right? Then in our solar system, we do know there's a sun, right? And we've got Mercury, Venus, Earth. Then we have Mars, a bit smaller. Then we've got the asteroid belt in between. Then we've got Jupiter, right? And then we've got Saturn with the rings, right? And then we've got Uranus, and then finally we've got Neptune, right at the end. So these are the rocky planets, right? Rocky, or also known as terrestrial planets, and these are the gas giants, right? And why we call these as planets? Because they revolve around the sun, right? Number one, and they have their independent moons, or they have a clear space in between them, right? They don't have lumps of rocks floating around them, right? They need to be alone, and those are called planets, right? So these are planets, and what other things are found in space are the comets, right? Comets are objects uh, which leave a trail, and they also move around the sun in larger orbits, right? They may just hit or crash somewhere, but usually they're just revolving around the sun. These are called comets. And asteroids are these lumps of rock which are hurled around, and around different paths, and they fall onto Earth. So these are asteroids. We've discussed comets, right? And oh, okay, let's just keep it as this, right? The comets. Now, when you look at the night sky, you see some shooting stars. We call those as meteors, right? Meteor shower. Some bigger ones are, fireballs. Exploding ones, exceptionally brighter ones, larger pieces of gases which may have material which might explode while it enters into this atmosphere, is called the bolide, right? And then the meteorite, if some of it does manage to not burn and reach the end of the earth and fall onto the surface, that piece of stone, which is just a space rock, right, is called a meteorite. So these are the same things, these four of them that I'm taking up, except depending upon where they are, and this meteorite which remains in space and does not fall on earth, right, it just moves closer and just maybe leave away. Micrometeorites, smaller stones, right, smaller fragment. Biggest ones are called asteroids. They may even come around, right? We do know the dinosaur killing asteroid that broke the planet into several of these continents that we see, right? So now our own moon, right? A little bit about our moon. I'll discuss this in more detail once you're in grade 8, because over there we will discuss the complete formation of moon. But just for you people to understand that moon has this clearer face which faces our side, right, which remains closer, faces our side, and the back side is where all the asteroids, right, hit. Asteroids, meteorites, right? All of these crash onto the surface of the moon. Not maybe asteroids previously, not quite recently. We haven't seen any asteroid, but meteorite strikes. These impacts are due to these. Space rocks, big space rocks, which fall onto the surface of moon. Right, the moon is protecting us, so that's why moon is important. So we'll be discussing this in year 8. Now, I hope I've covered most of the content of this topic. You just need to review and have a look at the context and the workbook, and you'll be just fine for the next topic. Right. Thank you.